right, so let's start our next session with Felice Torelli, apologize if I pronounced that wrong, from ESA, discussing file-based operations in the ESA JUICE mission.
Oh, in the back, you're back on.
All right, so can you hear me? Yeah. Good. So my name is Felice Torelli. I work at the European Space Agency at ESTEC, and today I will present a file-based operation in the JUICE mission. The work has been done together with Enrique Cal from Airbus Defence and Space, Ignacio Tanco from ESOC, and Christian Erd and Arnaud Bordeaux. So the agenda for the presentation is the following. I will make a very short overview of the JUICE mission. I will present the data handling subsystem, which is set the background for the discussion that comes up, which is the file-based operation itself. For who doesn't know, JUICE is the first ESA mission going to Jupiter. It will observe Jupiter as a system and the three of the moons, Galileo moons, Ganymede, Callisto, and Europa. And it has been launched in April last year, so it's almost 1 year in orbit, and now it's in its journey, 8 years long journey to Jupiter. So the spacecraft is rather big. At launch, it had more than 6 tons of launch mass. It has a very large solar array, 87 square meter, for getting just 800 watt end of life when we are at Jupiter. The mass memory is 1 terabit end of life, and we implement downlink capability on X and K band for about 50 kilobit per second when we will be at Jupiter. It implements a large suite of payloads. It has in situ payload for particles and plasma and magnetic observation. It has let's say a radar sounder, a laser altimeter, a camera, a high resolution camera, three spectrometer, and radio science also experiment on board. So it will perform a very comprehensive observation and exploration of the Jupiter system. To get there, it will take about 8 years. It will perform 4 gravity assists. The first one is coming up in August. It will be a lunar Earth gravity assist. Then it will do a Venus flyby, and other 2 Earth flyby to get there. And once he arrives at Jupiter, it will perform a Jupiter tour of about 35 moon flybys before actually inserting in orbit around Ganymede to perform observation of Ganymede in a circular orbit. One particular part of the mission is driven by the fact that we will have about 1.5 hours of round trip for commanding and telemetry. We will have we use X-band for telecom and telemetry, and K-band only for science telemetry. And the use of X and K-band was a trade-off to let's say get the best out of the best compromise between error rate, data rate and volume, and transmitting power on board. The data handling, the main unit implementing data handling is the Common Data Management Unit. Is made of onboard computer and a solid-state mass memory, both integrated on the same unit. The processor module in the OBC is where all the central software is running, so OCS, TMTC, thermal control, everything there. We have a telecom and telemetry implementing, as I said, decoding in X-band and encoding, telemetry encoding in X-band and K-band. And we have an onboard computer mass memory, small mass memory only for operational telemetry, which is based on packet store. On the mass memory module, we have a SwRI router, which is interface interconnecting the processor module, the science mass memory, and the instruments, and the science mass memory itself, which stores science data in the form of file organized in directory, and it supports also CFTP downlink. The instrument, most of them are packet terminal, are connected to to a SwRI network, and let's say, and then we have an additional instrument which is just a Ka band transponder for radio science, which is on Milbus, and I will not discuss about it further in the presentation. Looking into more in zooming into the mass memory itself, we have three main functions. We have the mass memory itself, which is flash memory based with some FPGA that manages the storage and the CFTP transaction. We have the redundant routers where they interconnected both mass memory modules that they are as well redundant, and the instrument and the processor modules as well. And cross-point switch, which are implementing a cross-trapping between the SwRI router and the instruments. Each instrument implements nominal and redundant SwRI interface, but we have different level of redundancy. Some instruments, like for example, Gala or Janus or Magis, implement dual redundancy inside the instrument. Others are single string, like UVS, which was developed here in Southwest, or RIME or RADEM are implementing are a single string with two SwRI going into the SwRI network. You see here the data generation rates are very different. So we have very let's say we have instruments like Janus or Magic that at the peak they can generate an high data rate, more than 50 megabit per second. And we have others that, like the magnetometer, for example, that generates 9 kilobit per second data. So a very different variety of data recorded in a mass memory. We have 16 computers on board, not counting the redundancy. The majority of them are on the payload. Each payload has its own data processing unit, its own computer. And it's not a coincidence that most of them are based on GR712 and they have a common boot, because with Geisler we implemented an activity to define a common design for the DPU and a common boot software validated once and distributed to the PIs for adopting this solution, and which was adopted by 7 to 8 instruments. Also, the fact that we use RTEMS 4.10 in most of the instruments was the result of a trade-off, let's say, shared with the payloads. And one instrument which has a notable exception is Magis, where CNES was managing the development, and they selected to use LVCOGen like NX Stratum, like Julian has described yesterday in his presentation. Going more into the focus of the presentation, we look into the file-based operation. In the SwRI network, we use logical addressing. We have one logical address per instrument for managing the telecommand. So every instrument has its own logical address for receiving telecommand. We have one logical address per instrument for the operational telemetry, so housekeeping events, things like that. And then we have one or more logical address associated to data stream for science data recording that are managed directly by the science mass memory. Science telemetry storage is based on data stream, which are identified with the SwRI logical address of the packets that are transmitted. Each stream, so therefore each logical address is associated to a directory in the mass memory, and the files in the mass memory are created automatically and switched by the central software based on maximum file size reached, a timeout, or an explicit command. So, for example, in this case, we have instrument 1 send packet with the logical address 0A and store data in the file, create and store data into the file of directory A. It manages another stream which sends data using logical address B to the directory B, and instrument 2, for example, generate data with logical address, specify logical address C, and store the data in the directory C. All of this is orchestrated and managed by the central software. The mass memory is a relatively simple unit. It has some FPGA with some logic implementing the fast, let's say, distribution of the data across to the various modules, to the various memory modules. But the file system, the file switching, the logical addresses management is all in the central software. We have one particular interesting aspect of the data storage, which is the need to associate observation with a file. For example, you take an image with a camera, you want that the image is all confined in one single file, not spread across different files. And to do that, we have three different mechanisms. We have the one based on mission timeline. If you can already, let's say, predict when the observation will take place, when it will start, when it will stop, we command it the start with on the mission timeline, and we command the switch of the file through a mission timeline. So very straightforward and easy to implement. We also let the instrument to manage the start of the observation and deciding when the observation has ended. So in this case, the observation is started by the instrument itself, and when the observation stops, the instrument generates an event to the central software, which reacts by switching the file. And then another observation can take place afterward. These are all cases where the observations are separated in time, so they are not continuous. If we have observations that are continuously generated, but we still want to be able to split the observation in file in a consistent way, we have a mechanism based on flip-flop, and therefore we have, for this observation, we associate two directories and two logical addresses to the observation, and therefore the instrument can start making the observation by writing into the file of the directory flip with logical address X, and when the observation stops, it generates an event and it starts the next observation back to back, but writing into the directory flop, therefore with logical address Y, for example. In the meantime, the central software will switch file on the directory flip, and therefore when the observation 2 ends, the instrument can start again feeding the data into with the logical address X. Telemetry downlink. Here we have a push concept, push approach. Each directory has an attribute in which RF band to implement the downlink, flags for eligibility for downlink, and a priority. And in this case, let's say, and directory with the same priority on the same RF band are actually managed in round robin. We downlink only closed file, and we use CFTP class 2 with deferred NAC for the transfer. So in this case, for example, we have the directory A as a X-band attribute, and it is in priority 1. It is transferred. The files are transferred to X-band to the X-band TM encoder, while, for example, directory C has K-band attribute, and it transfers in parallel to the K-band. And directory B has a K-band attribute, but priority 2, and it will start the downlink only when the directory C is complete, is empty. All the transfer on directory C are done. Here we see, with a different animation, the same concept. We see that we have a K-band and X-band the downlink happen in parallel because there are two separate channels, two separate queues. And in X-band here we have by directory A and directory B, which have the same priority, and therefore they are managed in round robin, one file each at a time. Once the file is confirmed to have been received successfully on ground, using the CFTP protocol, we authorize the automatic deletion of the file on board. So we have automatic management of this aspect. And in this case, for example, again, once the directory directory A and B with priority 1 are empty, is the time when we can start the downlink of the files from directory C, which has priority 2. And when a file appears, or one file is closed again on the directory A or B, we completed the downlink of the file that was being downloaded in directory C, and then we go back to directory B with priority 1. We implement also selected downlink, which is a mechanism that allows to filter or to select a subset of the files to be downlinked to ground. And we implement this by having two directories or two streams. We have the selector directory, which is where it contains small files, a sort of a thumbnail, which are downloaded all the time with high priority. And we have the high resolution data that are stored in the bulk directory, which are not set for downlink. So the data that are in this ping directory are not going to be downlinked automatically. But the PI, after receiving the data from the selector directory, can analyze the content and can decide in which time window he wants the file to be downlinked. So in this case, for example, we might have file 2 and file 4 from both directory 3 and 4 to be downlinked. In this case, they are requested to be selected and moved to a downlink directory such that they are downlinked to ground. So a summary, JUICE is the first interplanetary mission that is from ESA that is implementing natively the support for science file for science storage, downlink, and ground processing in an integral manner, which is streamlining a lot the operation and the science data distribution. We use logical addresses for different type of stream, telecom, telemetry, science telemetry. We use, let's say, the logical addresses are associated to directory, and we use attribute on the directory to manage the CFTP and the downlink. We have different ways of storing files and synchronizing file with observation, with mission timeline, with events or flip-flop and events, and we support also selected downlink. We have 16 computers on board, mostly Leon 2 or Leon 3, and the mass memory is integrated in the onboard computer in the CDMU, and it has end of life 1 terabit of size. Maybe one bonus slide regarding the future of file-based operation at ESA. JUICE was one of the trailblazer missions, one of the first where we used this file-based operations approach. But now all the missions that we are implementing are following this mechanism. This is used in Plato, Ariel, Envision, LISA, and this is done thanks to the fact that at ESOC and at ESA in general, we standardized this concept in the operational interface requirement document in the new revision of PUS ECSS standard, and therefore it will be applied to all the missions in the future. And that's all for today. Thank you.
All right, well, I'll ask an online one first. If you could describe, if you use NAND, and if you could describe if there's any if you could describe the file metadata.
So let's say the file system is managed by the core software from Airbus. It has, let's say, typical metadata like the creation date, file name. The file name is done by two integers, so it's a very simple system. And then, let's say, other metadata, let's say, are embedded in the file system, typical from an Airbus class of software.
we'll take one more. There's a question. Oh, Isaiah Garrett is typing. Do you want to just ask the question? Okay. All right. Can you compare the cases where if there's an instrument that can produce data faster than you can save it? Is that an issue?
Not really, because let's say as we shaped or we defined the mass memory in a way that can manage the peak data throughput, which is the combination of all these data peak, which will now not happen in actually all at the same time, and in some cases or in some cases for a short period of time. The router have two links at 100 megabits per second signaling rate into the mass memory, so the mass memory can manage up to 160 megabits per second, which will never reach by the instrument in their peak data generation.
Okay. Well, thank you very much, Felice. I appreciate it. Thank you.